Hey there, welcome. If you've ever looked at a weather map, you might have noticed something, well, kind of weird. High up in the atmosphere, thousands of feet above us, the wind just doesn't seem to follow the rules we'd expect. Today, we're going to unravel the really elegant physics behind why these high altitude winds do what they do. Okay, let's just jump right into the big puzzle here. We all learn that things move from high pressure to low pressure. That just makes sense, right? So, why is it that when we look at the winds way up there, they seem to completely ignore this rule? They just flow sideways, almost perfectly tracing those lines of equal pressure, which are called isobars. It really seems to defy logic, but it's the absolute key to understanding our atmosphere. So, here's how we're going to crack this thing open. We'll start with the initial push that gets the air moving. Then we'll see how our planet's spin throws a major curveball into the mix. We'll watch as these two forces find a kind of perfect balance. And finally, we'll see how this whole elegant dance helps us, actually read the sky. All right, first things first. Before anything can move, it needs a push, right? Well, think of this next force as the engine that starts up all air movement on the planet. This is a force you're already familiar with, even if you've never heard its formal name. It's called the pressure gradient force, or PGF for short. It's really just the atmosphere trying to even itself out. Air is always getting pushed from a packed, high-pressure zone towards a less dense, low-pressure one. And honestly, if the Earth didn't spin, that would be it. All winds would just flow directly from high to low. But, of course, that's not the whole story. Okay, now it's time to bring in the second major player in our story, and this is the one that makes things really, really interesting. Now, this isn't a force like gravity. It's what's called an apparent force, which is really just a side effect of living on a big spinning ball. Just picture this. You're on a spinning merry-go-round, and you try to roll a ball straight to your friend on the other side. From your point of view on the ride, it's going to look like the ball just curves away on its own. That's the Coriolis force in a nutshell. Any object moving over a long distance on Earth, air, ocean currents, you name it, gets deflected because the ground is literally rotating out from underneath it. So this force has a few key rules, and they're pretty straightforward. In the northern hemisphere, where we are, it always pulls things to the right of their motion. Down in the southern hemisphere, it's the exact opposite, a pull to the left. At the equator, there's no effect at all. And this last one, this is the absolute key to the whole thing. The faster something is moving, the stronger that Coriolis deflection gets. Remember that. So we have one force pushing and another one deflecting. So what happens when they meet up high in the atmosphere where there's no friction from mountains or trees to get in the way? Well, they perform this really delicate dance that ends up in a perfect state of equilibrium. Let's walk through this dance step by step. Imagine a little parcel of air just sitting there. First, the pressure gradient force gives it a shove, straight towards the low pressure. Simple enough. But as soon as it starts moving, the Coriolis force kicks in and starts nudging it to the right. As the air picks up speed, that Coriolis deflection gets stronger and stronger, pulling it further and further to the right. And this goes on until a magical point is reached. The wind has turned so much that it's now flowing parallel to the pressure lines, with the PGF pulling it one way and the Coriolis force pulling it equally hard in the opposite direction. And this beautiful state of equilibrium, it has a name. Meteorologists call it geostrophic balance. The push towards low pressure is perfectly canceled out by the deflection from the Earth's spin. And the wind that you get from this balance, that's called a geostrophic wind, which literally means Earth turned. Pretty cool, huh? And there you have it, the final result. Because the forces are in balance, there's no net force left over to speed the wind up or slow it down. It just coasts. It's like it's trapped on a highway, defined by those lines of constant pressure. And that is why high-altitude winds blow sideways, solving our big puzzle from the beginning. Now, this isn't just some cool bit of physics trivia. It's actually a super powerful tool that meteorologists use every single day. Understanding geostrophic balance lets us look at a weather map and instantly know what the winds are doing thousands of feet up. It's actually a really simple relationship. The strength of that initial push, the PGF, is all about how close those isobars are to each other. If they're packed tightly together, that means you've got a steep pressure gradient, a strong push, and, therefore, very strong winds. If the isobars are spread way far apart, the push is weak, and the winds are going to be light. So just by glancing at a map, you can get a really good idea of the wind speed. And this whole idea leads to one of the coolest and oldest tricks in the meteorology book, Buys Ballot's law. Because the wind flows with low pressure on its left and high pressure on its right, in the northern hemisphere anyway, you can literally figure out the entire pressure system just by standing with the wind at your back. It's a direct result of geostrophic flow. Okay, so it's important to remember we've been talking about a pretty ideal situation here. The geostrophic wind is a perfect model, but the real world, especially down here near the ground, has a few more wrinkles. So what's the big difference maker between winds way up there and the winds we feel down here? Well, it all comes down to one word: friction. Up high, there's basically nothing to slow the air down, but at the surface, wind is dragging against trees, buildings, mountains, everything. This friction slows the wind down. And remember our rule? A slower wind means a weaker Coriolis force, and that throws the whole perfect balance off. The PGF wins the tug of war, and the wind starts to leak across the isobars toward the low-pressure center. All right, so let's do a quick flyby of the big takeaways. The geostrophic wind is what happens high above the Earth's surface, where friction isn't really a factor. It's that perfect balance between the push of pressure and the spin of the Earth. This balance creates winds that flow in straight paths, parallel to the isobars, and it gives us an awesome model for what's really happening in the upper atmosphere. So we've totally nailed how this works for straight-line winds. But when's the last time you saw a weather map with perfectly straight lines? They're always curving around high and low pressure centers. So what happens to our perfect little balance when the wind has to constantly turn? Well, that is a fantastic question for another time. Thanks for joining me.